Welcome back. Myself Dr. Sayanti Chatterjee, the faculty of IARE College, Hyderabad, of Triple Department. Today my topic is magnetic polarization, and today we will discuss about the magnetic polarization. So before starting, what is polarization? Polarization can be classified into two parts. One is called the electric field polarization. Another one is called the magnetic field polarization. Electric field polarization and magnetic field polarization. Today our main discuss will be the magnetic field polarization. So before starting the magnetic field polarization, we will give a small glance of electric field polarization, and then we will go to the magnetic field polarization. So today our main aim is the magnetic field polarization. So when the question comes what is field? Field is nothing but an area where if we keep one electric charge or magnetic pole, it will feel some force. So electric field and magnetic field electric field means due to a current carrying conductor, we will get an area, and if we in that area if we keep an electric charge, it will feel some force. So the polarization means if we have an atom, it has for the electric field where I am telling, it has the positive pole and negative pole. If we connect the atom with any battery source or we keep it in a field, what will happen? The positive charge will come in the same side and negative charge will go in the another side. As a result, the atom will be elongated, it will be big, and this is called the polarization. So electric field, this is the polarization, electric field and magnetic field polarization. So before starting, I will just give a small demo of the electric field polarization. So an electric dipole is formed when 2 point charges of equal magnitude but opposite signs are separated by a small distance. When an electric field E is applied, the positive charge is displaced from the equilibrium position in the direction of the E, and the force F is equal to plus QE. So if we want to make it elaborate, you can think there is a two charges plus Q and minus Q, and their distance is D between them. Then the distance traveled by called the product of the charges and distance traveled by the charges is known as the electric dipole. What is electric dipole? The product of the charge and the distance traveled by them is known as the electric dipole. So P is equal to Q into D, where P is the electric dipole moment, D is the distance between the opposite charges. The line between two charges is called as the axis of dipole. So now we will discuss about the magnetic moment. So what is magnetic moment? Now we will come to the magnetic field. What is magnetic moment? Magnetic moment, also known as the magnetic dipole moment. So this is the two terms, magnetic moment, also known as the magnetic dipole moment. Magnetic dipole moment is the measure of the object's tendency to align with the magnetic field. So magnetic moment, also known as the magnetic dipole moment, is the measure of object's tendency to align with the magnetic field. Magnetic moment is defined as the magnetic strength and orientation of a magnet or the object produces a magnetic field. Magnetic moment is defined as a magnetic strength and orientation of a magnet or other object that produces a magnet field. What does it mean? See, we are taking one example. We have an iron bar. In the iron bar, there are many poles are there. There are many poles are there. So all the atoms has the north pole and south pole, north pole and south pole. Now, if we are keeping the magnet in a magnetic field, if we keep it in a magnetic field, what will happen? The magnet will rotate itself and turn such that if this is the south pole, final south pole and final north pole, what will happen? All the atoms will be like north pole and south pole. All the atoms will be like north pole and south pole. So they will align themselves. The orientation of the magnet or other object produces a magnetic field. It will increase the magnetic field. So this orientation, the moment, is known as the magnetic moment. Now, if we take this magnetic material, if it is a permanent magnet, no change. But if we take this magnetic material out of the magnetic area, what will happen? It will if we take it out of the magnetic area, what will happen? It will there will be some magnets will change its position, but maximum magnet will be in the orientation of a north and south, and it has some small magnetic field always present in the magnetic material. Not magnet. I am telling about the magnetic material. If we remove the magnetic material from the magnetic field, little amount of magnet will stay in it, and this is known as the residual magnetism. And that's why this is the main working principle of the self-started DC motor, like the self-shunted DC motor, like the shunt and series DC motor. So, the magnetic moment is a vector quantity. It has always a direction. The object have a tendency to place themselves in such a way that the magnetic moment vector becomes parallel to the vector field of lines. As I told earlier in the diagram, that it has a tendency, if it is a magnet, it has a tendency to align the vector themselves in the direction of the north pole and south pole, or parallel to the magnetic field lines. The direction of the magnetic moment points from always south to north pole of a magnet. It is always, though I draw it, so it is a wrong drawing. It will be always, the drawing should be always from south to north. The magnetic moment's direction will be always from the south to north pole. The magnetic field created by a magnet is directly proportional to the magnetic moment. The magnetic field created by a magnet is directly proportional to the magnetic moment. So we can write tau. Tau is the magnetic moment, is equal to m. Tau is the magnetic force, magnetic moment, into B. B is the flux density. So what is the magnetic moment unit? We can see from the last one, tau is equal to m into B. M is equal to, so in the definition of the current loop, magnetic moment is the product of current flowing in the area. So what is the meaning of magnetic moment? The strength of the magnetic moment depends on the how much current is flowing for an electromagnet. As this is an electromagnetic field theory, we will always concentrate on the electromagnet, and in case of the electromagnet, the magnetic strength depends on the amount of current and area on which the current is flowing. So M is equal to I into A. So we can write the unit is equal to ampere per meter square. Ampere meter square, not per, ampere meter square. It is also suggested in terms of torque and moment. So we can write it in the previous, we saw in the previous slide. If we go in the previous slide, we got that the torque is equal to magnetic moment into B. So magnetic moment is equal to torque into B. Torque means work done, so its unit is joule, per B is the Tesla. So we can also write that torque is measured in the joules and the magnetic field in the Tesla. So the unit is the joule per Tesla. So this is due to the, we can tell this is the magnetic definition. The definition with respect to the perspective of the magnets. This is for the electromagnet. So you can use any of the definition. Magnetic moment unit is equal to current flowing and the area M equals to I into A. So next is the magnetic dipole. Magnetic dipole is formed when two opposite magnetic charges are separated by a distance L. So this is plus qm, this is minus qm, and distance between them is L. So this is plus qm minus qm. As we are taking an electromagnet, current is flowing. So the line joining two charges is termed as the axis of dipole. The direction of the magnetic dipole is always minus qm to plus qm. And the magnetic moment can be written as the M is equal to qm into I. Now there is one point that qm, the unit is worsted. The charge or the pole strength of a magnet cannot be separately calculated. A magnet is always, it has a two poles. Those we are writing mathematically plus qm and minus qm is correct, but we cannot write it in a single variation. Next is the write the expression of the magnetic dipole moment. The line joining, as we discussed in the electric dipole moment in the previous slide, this is same as the electric dipole moment. If there is a two charges of the same value, if it is plus 2 worsted, if it is minus 2 worsted, means are the same value and their distance is L, then we can write that the magnetic dipole moment M is equal to qm into L. M is equal to qm, the pole strength qm, into L is the distance. M is the magnetic moment. Small m is the magnetic dipole moment is equal to qm into L. And as I discussed in the previous slides also, if we are thinking about an electromagnet or a bar conductor allowing I current to flow in a loop. So there we can write M is equal to I current into A ampere. So numerically for one magnet, both are equal and we can write qm into L is equal to I into A. Or we can write magnetic strength into length or distance between these two is equal to current into cross-sectional area. So we can write this also. That when current is flowing for an electromagnet, when current is flowing through a loop, how we make a electromagnet? I told in the last my lecture that electromagnet is two types. One is the bar type, another one is the horseshoe type, or we can tell solenoid and toroid type. We are giving the connections current, and we are giving, when we are giving the connection current on an electromagnetic material, it will turns into the magnet. The north pole and south pole will generate. So magnetic dipole moment depends on the amount of current and the area. So we can write M is equal to I into A, and QM is equal to M is equal to L into A, and QM is equal into L is equal to I into A, and both are numerically equal. Now what is magnetization? So when we are giving the force, we are giving the magnetic moment, if there exists a conductor consists of number of dipoles in its volume, then the magnetic dipole per unit volume is known as the magnetization. We are telling it is magnetized, it is magnetized. What is the meaning of magnetized? If say this is one bar, again I am taking the example of a bar. So in the bar there are the, so all are from the south pole to north pole. So all the atoms are due to the magnetic moment, they have arranged themselves such a way that all the magnets has been changed into the parallel to the magnetic lines of force. Okay, so what is the magnetization? The magnetic dipole moment per unit volume, how much magnetic poles has been arranged, that is known as the magnetization. So what is magnetization? If there exists an conductor consisting of number of dipole in its volume, then the magnetic dipole moment, so then the magnet dipole moment per unit volume is called as the magnetization. The magnetic dipole moment per unit volume is called as the magnetic moment. So capital M is equal to small m into V. Now what is capital M? From the previous section we know QM into L. QM into L. What is the meaning of a volume? Volume means area. L is the, what is L? L is the length between the north pole and south pole. So QM into L. And what is area? What is volume? Cross sectional area into length. So length will be cancelled out and it will be QM into M. And the unit will be worsted per meter square. So this is the magnetization. What is magnetization? Magnetization means the amount of the magnetic charge per unit area. So if we want to make a difference between the electric dipole and magnetic dipole consists of two equal and unlike poles that do not have separate existence, whereas the electric pole has two equal and opposite charges that have separate existence. Electric dipole and magnetic dipole is there two equal and opposite charges in an electric dipole with separate existence, but practically two unlike poles, two separate poles never exists. An electric dipole can be described as a couple of opposite charges plus Q and minus Q. They are separated by D. In the magnetic dipole can be described as a magnetic north pole and the south pole are separated by a small distance L. Electric dipole has two equal and opposite charge. Magnetic dipole has two equal and unlike charge. Now we will discuss about the application. And there is another important thing is the expression of the torque due to the moving charge. So the expression of torque due to the moving charge means when there is a charge, there is an expression of torque due to the moving charge. So you can see this is our axis A, B, C, D and distance between them is D. This is the axis of rotation. There are some charge. So the expression of torque due to moving charge depends on the field strength T into B. Now what is torque? Torque is equal to T 2 into torque on each side. This is a torque, this is a torque. So torque into two sides. T and this is also T. So T is equal to torque on each side and equals to what is the torque definition? Torque definition is equal to force into distance from the axis of rotation. So if this is a magnet, the distance of rotation is the midpoint. So from the midpoint, what is the distance? We have to calculate. Now force is F if the distance is D. If the distance is D, so the midpoint is, this is D by 2. F is equal to D by 2. Now what is the force? Force is equal to, we can write, so we can write it F into D. And what is F? F is equal to, according to the Lorentz force, BIL cos theta. Theta is the angle, or we can write also BIL sin theta. We have used here beta. Beta is the angle of the rotation with the lines, axis of rotation with the magnetic lines of force. So BIL cos beta into D. So L into D, what is L? Length into D is the nothing but the cross-sectional area. So we can write BIA cos beta. BIA cos beta. This is the torque due to the moving charge due to the magnetic moment in a magnetic material. Next we will discuss about the characteristics of the permanent magnets. Permanent magnets are the one which readily available in the nature. Permanent magnet are one which is readily available in the nature in the form of bar and the horseshoe shape. The permanent magnet, irrespective of supply, always exhibits the magnetic properties. Permanent magnets always develop a constant magnetic field. As the pole strength of the magnetic field is constant, it always shows the constant magnetic field. Next is the strength of the permanent magnet measured on their cohesive force. How much is the force of attraction and repulsion? Magnet with high cohesive force have the longer life. But what is the disadvantage of the permanent magnet? The main disadvantage of the permanent magnet is the aging effect. Long run, they due to the rust and due to the other environmental problems, it may got the damaged. Now what is inductance? When the magnetic field comes, it always comes the inductance. What is inductance? The voltage across an inductor is directly proportional to the rate of change of electric current. Rate of change of electric current flowing through the inductor. We can write V is equal to L di by dt, where V is the instantaneous voltage across the inductor in volts, L is equal to inductance in Henry, and di by dt is equal to rate of change of electric current in ampere per second. Inductance are basically two types, as I discussed earlier also. One is called the self-inductance and another one is called the mutual inductance. Today we will discuss the self-inductance for a solenoid. So what is the self-inductance of a solenoid? Let us consider a solenoid as shown in the figure. Okay, so we are considering a solenoid whose length is L. What is the meaning of the solenoid? Solenoid means these two parts, it will be mounted on a bar and the two sides are open-ended. For a toroid, the two sides are close-ended. Here you can see this one and this one are open-ended. So say this is our north pole and this is our south pole. So, is that we are thinking that the number of turns N is the number of turns per unit length, and capital N is equal to the total number of magnetic field density inside the solenoid. So, we know flux density B is equal to, we can write H is equal to N into I. If I current is flowing, we can write H is equal to N into I, number of turns into current. So what is B? B is equal to mu naught Ni. Now what is mu naught? And so because B is equal to mu naught into H. Mu naught is nothing but the permeability of the medium. So what is inductance? Inductance L is equal to N phi by A. N phi by A. So if we write it, L is equal to N phi by I. What is phi? Phi is nothing but the B into A. What is B? Mu naught N I into A. So N B, I am writing here, then it will be easy for you. L. So if we take it, mu naught N I into A. What is N? N is nothing but the total turns. So N is equal to N into L mu naught N into I by A. What is N? Again we can write it like NL mu naught NL by L into A. What is N into L? N into L is nothing but the capital N. So we can write N mu naught capital N A by L, or we can write it N square mu naught N square A by L. Mu naught N square A by L Henry is the inductance of a solenoid. So first we are taking the total length is L. We are taking capital N is equal to number of turns, and we are getting the north pole and south pole, and number of turns per meter is N is equal to capital N into L. Next we will discuss about the same thing about a toroid. Let us we have a toroid. Toroid means a circular path. Toroid is nothing but a circular path. And we are taking the number of turns is capital N. And the current flowing through it is I. So magnetic flux inside this is B is equal to mu naught Ni by L. Actually mu naught small ni, B is equal to mu naught small ni, capital small n means capital N into I. What is L for a circle? If you can see this yellow one, it is the radius. If the radius is R, then we can write length is equal to 2 pi R. So what is the inductance? Inductance is similarly, if we again put the value L is equal to N phi by I, and what is N phi by I, and what is phi? Phi is nothing but the N into B into A. So if we put the value, we will get N square mu naught capital R square. Capital R is the outer radius. Capital R is the outer radius showing in the green. And for calculation of A, we are getting this by 2R into H. So this is the self-inductance of a toroid. Now, energy stored in an inductor. Say when current is flowing, there is a let us work done increase is di is dw. So by the law of conservation of energy, we know power, if we are taking only the DC, we are thinking about the DC, not AC. So what is power? Power is equal to voltage in or current, or we can tell instantaneous voltage into instantaneous current. Small v always tells the instantaneous voltage, and small I always refers to the instantaneous current. So we have the instantaneous voltage into instantaneous current. So what is the instantaneous power? Power is equal to V into I. So what will be the energy? Energy will be power into time. So energy is nothing but the work done. So we can write dW is equal to dw is equal to vi into dt. What is v? V is equal to li di into dt by dt, because we know voltage. What is the voltage? In the case of the voltage, v is equal to l di by dt. So in the place of v, we are writing l di by dt, and I dt is always there. So it is coming L di by dt into I into di into dt. So dt will cancel out, and it will be the dw is equal to li di. We got dw is equal to li di. This is the instantaneous work done when current flows through an inductor. So what will be the total work done? Total work done means if we take the integration in the both side, and we will get half li square. Li di is equal to work done is equal to L half li square. Again, we know that the what is inductance? Inductance is equal to number of flux by I, n phi by I. So we can also express the same thing by W is equal to psi square by 2L. Psi square by 2L. This is the another procedure to write the equation. Psi square by 2L. But generally we write the work done is equal to half Li square. Now we will go for a problem. Let us have a solenoid of 300 tons of 300 mm long and 30 mm in diameter. If the current is 500 milliampere, calculate the inductance and energy stored in the solenoid. So first we will start the say this is an solenoid, and as we told that it has a diameter, so it looks like a cylinder, and there are some conductor on it. So number of turns is equal to 300. D is equal to 30 millimeter. So 30 into 10 to the power minus 4 meter square. A is the cross sectional area is equal to pi d square by r, and D is in the 30 into 10 to the power minus 4. L is equal to 300 millimeter is equal to 0.3 N. So inductance, as we discussed in the previous slide, inductance is equal to mu N square A by L. N is equal to 300, A is equal to pi d square by r. L is equal to L 0.3, and if we put the value, we will get 2.66 into 10 to the power minus 4 Henry. So this is the one problem, the energy this calculation. Next is the energy calculation of the solenoid. As we discussed earlier also the same thing. Okay, here mu value we have taken is 4 pi into 10 to the power minus 7, as this is the permeability of the air. Next is the energy stored in the solenoid. How to calculate? Already we calculate in the previous part the inductance. So work done is equal to half Li square. So L value we have taken in the last slide 2.66 into 10 to the power minus 4, and current is given in the 500 milliampere whole square. And after this solving, we will get 3.32 into 10 to the power minus 5, and the unit will be joule. So this is the one example of a solenoid. Next, two mutually coupled coils are connected in series. L1 is equal to 0.5 Henry, L2 is equal to 0.6 Henry, and the mutual inductance of them is equal to 0.1 Henry. Current flowing through it is increasing at the rate of 1 ampere per second. Means di by dt is equal to 1 ampere per second. Derive the expression for voltage inductance coils when they are in series adding and when they are in the series opposite connection. So first, this is the series adding. You can see that current are coming and this is the same direction. So this is the series adding and this is the series opposing. This current is in this direction and this is the series opposing. The series adding means L is equal to L1 plus L2 plus 2M. L1 is given as 0.5, L2 is given as 0.6, M is given to 1. So it is coming 0.5 plus 0.6 plus 2 into 0.1. So it is 0.5 plus 0.6, 1.1 plus 0.2, 1.3 Henry. What is V? Then 1.3 Henry into di by dt is 1 ampere per second. So it will come 1.3 voltage. Similarly, L is equal to L1 plus L2 minus 2M. So 0.5 plus 0.6 minus 0.2. So it is coming 0.9 Henry. So what is B? L di by dt 0.9 into 1 is equal to 0.9 volt. So these are the two inductance. They are connected in series adding and series opposing. This is the last questions of my today's lecture. So a very long solenoid of 2 into 2 centimeter are cross-sectional area of an iron core of 4,000 tons. If it carries 500 milliampere current and its permeability of the iron is 1000, calculate the self-inductance per meter and energy stored per meter. So this is the rectangular in nature and this is the rectangular in the nature. It is the 2 into 2. The cross sectional is 2 into 2 and it is in the this is solenoid. So number of turns is 4. So 2 into 2 means 4 centimeter square, means 4 into 10 to the power minus 4 meter square. Length is given as 1 meter, because the self inductance per meter we have to calculate. So L is equal to mu naught n square A by L. So we have to calculate here L by L. Mu naught value is, what is the mu naught value we will take? Mu naught value is 4 pi into 10 to the power minus 7. But we are not taking that. It is an iron. So it is a permeability is given as 1000. So there is a small change, mu naught mu r n square A by L. So 4 pi into 10 to the power minus 7 into 1000 into n square. N square is 4000 square into 4 into 10 to the power minus 4. And if we put the value, we will get 8.042 Henry per meter square. Next part is the energy stored in the same problem. Energy stored per meter. So what is the energy stored per meter? Energy is equal to half Li square half L. L value we know, L value we got 8.042 into what is the value of I? I is 500 milliampere. So if we put the value, we can get the energy stored. Similar, another problem is the mean radius of a toroid is 10 centimeter and the number of turns is 500. If the current flowing through it is 0.1, calculate the value of the magnetic field. So mean radius is given 0.1, number of turns is 500. So this is the toroid, it is the turns on it. Current is 0.1 ampere. So number of turns per meter is N by 2 pi r. So if we calculate number of turns, and we know we have to get only the magnetic field, not the inductance. So we have to calculate only B. B is equal to mu naught Ni. So if we put the value, we will get B is equal to 10 to the power minus 4 Tesla. There are two identical coils, A and B are there. They have 1000 turns each line in parallel plane such that 80% of. So when there are 10,000 turns means number of turns is 10,000. So M12 is equal to N1 into phi 12. So what is the current? The flux is 0.05. N1 is equal to 10. N1 is equal to 10,000. So 10,000 the flux is, total flux is 10,000 into phi 12. And the total flux linkage in the second coil is the 80%. So 80% of 0.05 milliweber. So next M12 will be the 0.05 of the 80 milliweber. So this is the answer. Last, the two inductors whose self-inductance is 75 millihenry and 55 millihenry, they are positioned each other on a common magnetic core so that 75% of the lines of flux from the first coil are cutting the second coil. Calculate the total mutual inductance of the two coils. So we know M is equal to K root of L1 into L2. So M is equal to 75% means 0.75 millihenry into 55 millihenry. So inductance is 48.2 millihenry. So they are in the same common place and total 75% of flux is connecting from first one to second one. So today we have discussed number 1 is the what is polarization, what is electric dipole moment, a small intro, then magnetic moment, magnetization, magnetic torque. Then we have discussed the applications of the magnetization, inductance, what is self-inductance of a toroid, self-inductance of a solenoid, energy stored, and some problems. So these are my today's topic, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.